Good morning, everyone. My name is Neil Mullen. I'm a software development manager with Lambda. I've been with AWS about 6 years, 5 of that with DynamoDB, and in more recent times, Lambda. My teams own a bunch of the back-end services on Lambda, and fundamentally, I own the scheduling problem as what we decide to run where when you do invocations against Lambda, which makes for a pretty interesting problem space. Today, I'm here to talk about big data analytics and machine learning on Lambda. I'll move to the agenda. I want to talk through fundamentally what kind of design patterns we see customers using Lambda for to process big data workflows and help you see what customers are doing. I want to talk through some of our own experiences doing this kind of thing with the massive data sources that services like Lambda are, how we've used those design patterns to get value out of it, and some of the lessons we've learned on that journey. And finally, I want to take a similar path with machine learning inference, show you how easy this is to do on a serverless architecture and why it's quite compelling, and talk through again some of the design patterns that we see ourselves and other customers using for this. And then finally, how we've actually used it internally ourselves in some of the services backing AWS Lambda. So with that, we'll move on to talking about this. So why is serverless a good platform is where I want to start. Increasingly we see modern analytics pipelines are pulling multiple large data sources, merging them, aggregating them, and pushing that data around. And serverless platforms make a really compelling environment to do that in. They scale up and down easily. They can handle data that is both infrequent as well as streamed, and put that all together at a minimal cost to you because you're not paying for idle. So the two key types of data we see in these big data analytics platforms. There's streaming data, which is your consistent data coming in, be it from a log source or otherwise, through something like Kinesis into the system. Or there's batch data, where you've data that isn't consistent. It's coming in chunks, it's time-based, maybe even another data source that's aggregating once every period, be it an hour or otherwise, that is pushing data in, or you've a data lake that is getting updated and you want to pull it in and re-aggregate once that has occurred. We'll talk through the theory quickly as to how we deal with some of these, and then we'll move on to the practical stories as to what we've done with it. And finally, a category on its own increasingly that we see on serverless architectures is MapReduce. It's a very common problem space, one that delivers a lot of value. So we want to talk through that separately. And again, how Lambda and serverless-based environments can make for a very powerful MapReduce engine. So very quickly, to just give the background on data streaming for those who aren't overly familiar with it. We're talking here about any kind of continuous data flow. So take the example of log files, for example. We pump those generally into Kinesis, which provides our streaming platform at AWS. And each Kinesis stream is made up of shards, which you can do up to 5 reads and writes of up to 2 and 1 megabytes a second, respectively. And you can pull from this data for up to 24 hours. And basically, Kinesis provides that consistent streaming platform into whatever we want to do with it. So the general design pattern we see here is that we have our input, our producer application, whatever it is, a service sitting on EC2 or otherwise, or even another serverless application itself, that is pushing records into Kinesis. And we're getting AWS Lambda to pick up those records from Kinesis. And in terms of putting this together, it's super easy. I mean, it's simply you create a stream on Kinesis, and you create an event source mapping to Lambda from that. And it's this easy. 2 quick commands, and you're up and running with a massively, I'm not going to use the word infinitely, but in that territory, scalable solution that will pull from your log sources consistently, scale with them as your service grows. On the second side, we're talking about batch processing, which is your more traditional data analytics pipeline. In this case, we're talking about some kind of trigger as when you want to pull on your data and when you want Lambda to act against that. The use cases we have here, such as processing log files, auto-indexing contents of a directory. And secondly, a periodical that you define. And the common use cases here is you have a large data lake sitting in S3 or something like that, and you want to re-aggregate or recompute the information against that once some change has occurred. So these are the kind of design patterns. This is one of AWS's batch analysis reference cases. But this is the kind of function you see Lambda perform within this serverless pipeline. That you've got an S3 manifest file where we simply define a trigger that on some action against an S3 object, it will automatically trigger a Lambda function that will feed your your data pipeline. In terms of defining this, it's super easy. You actually define the trigger on the S3 side so that you tell your bucket that when there's a configuration change, it will trigger a Lambda function. And it's simply a case of mapping your Lambda ARN to the S3 bucket. You can do it with an SDK as easily as you can with a CLI. This is the Python interface. But it's a couple of simple lines, and you're up and running with this data pipeline. The second side of it, and perhaps the more common one, particularly when working with data lakes, is the idea that you will periodically trigger Lambda when something occurs. And there's the traditional side of things where you can simply use something as simple as a cron expression that you will be familiar with, or you can have CloudWatch events do the work for you and trigger Lambda. Because of the nature of this, that it's bursty and it's batch-based, we tend to put a queue in the middle to smooth out some of that burstiness and start to feed into the fan-out we have from Lambda. And then we use those Lambdas to perform whatever kind of aggregation we want and trigger as many of them as we need from this queue to push the data to whatever data source we eventually want to consume it from, whether that be a re-updated source in S3 or to push it into something like DynamoDB or Elasticache where we want faster aggregated data access to feed our applications. In terms of setting this up, you can do it both with a traditional cron expression or setting up something like defining a fixed rate of minutes through the console. It's equally easy from an API or a command line. You literally can use human-readable expressions like every 5 minutes, I just want to run this. And there you have your scalable pipeline fed with Lambda pulling from it whenever you want. So finally, the other area I wanted to talk to quickly to give us the background for all of this is MapReduce. And MapReduce is basically the use of a parallel or distributed algorithm to crunch large data sets where we can break the problem up into a mapper and a reducer to basically pull the data, aggregate it, and then do the reduction on the data afterwards. Simple use cases like counting and summing data, collating and sorting, or getting distinct values from our data. And the power of MapReduce is it allows us to use a large number of fairly simple machines to do the kind of crunching which in the old days would have required big, expensive machines. And nowadays we can do it with serverless, which makes it even cheaper again because we can scale up and down with the needs for that reduction. And where MapReduce starts to come into itself is you can do distributed task execution. You can do cross-correlation, which gives you powerful things like text analysis. Or more importantly, for most of the kind of problem spaces we deal with, you can use MapReduce to do graph analysis, which opens up a huge problem space to you. One example we have is Fannie Mae are using serverless HPC and MapReduce for Monte Carlo simulations. So that's the kind of power you can get on a serverless architecture with this stuff. And in terms of setting it up, this is what it tends to look like. That you, excuse me, you have an input data source coming from S3, which is triggering a set of Lambda mappers. Those mappers perform the initial crunching of the data and push that into another S3 bucket. We use the kind of S3 trigger we just discussed a few minutes ago to again trigger a second round of Lambda functions to do the reduction of that data that we've pushed into S3 and pull the final result out into a bucket. And this is a super powerful configuration that we can put together quite easily with a couple of small Lambda functions. So let's take a look at what those look like. So to do something like this, we're looking at about 40 lines of code total. Here's a mapper and a reducer, which will scale as wide as we want, depending on the volume of the input data. This comes from the reference configuration listed in the GitHub link at the bottom. And you can use this to crunch as much data as you like very easily with very little code here. What's getting even better is what we announced on Wednesday. We now have S3 Select in the mix. So historically, we would have had to pull all our data from S3 when we're doing this mapping phase. Whereas now, we can simply pull the columns we want and get some of the heavy lifting work of that mapping phase done on the S3 storage hosts themselves. If you've got a wide data set with a large number of columns that you're only interested in doing the MapReduce against a small portion of that, you can pull just the 2 to 3 columns you need and reduce reduce the working data set significantly. From the templated use case we have here that we saw the code from the previous slide, we're seeing improvements of about 400% on execution time using S3 select over the existing pull everything and do the crunching. So historically, we were doing this kind of thing where we're pulling all of the code and we're just doing a get from S3 and then we're doing a split on that where we're pulling out the two fields that we're interested in, field 0 and 8 in this case. So we're pulling everything else in the middle for every single line we want there. Whereas now, we can simply do a query to S3 and pull just the fields we want. In this case, you use the S3 select interface in another function, which simply defines a select expression. So we're selecting column 1 and column 4 from the S3 object. All of that is done on the S3 server. You're only paying for the reduced amount of data that comes over the wire, and you're paying for significantly less execution time on the Lambda side as it deals with that after the fact. So that's kind of, I wanted to relatively quickly move through some of the key design patterns from the stream transformations through big data analytics, through MapReduce. So we've a bit of common terminology as to the kind of work we're doing in serverless big data analytics. And using that, I want to talk through some of the systems we've built and how we've solved some of these problems and what problems we've had along the way. So hopefully you can avoid some of the similar problems, some similar problems. The first of these that we want to talk about is, sorry, I've just summarized all that. Apologies, I'm a slide ahead of myself. Okay, everything I've just said. Sorry, the first of these systems is a system we call Lambda Stats. And in this case, Lambda represents a huge big data source, which is why I felt it made for a great story to talk about here today. We have vast numbers of invokes happening every second, coming into a fleet of many, many thousands on the front of Lambda, which we have to figure out the scheduling for, again, the problem space I own, as to where we're going to execute each of those functions. But most importantly, any customer who's doing many, many invokes against Lambda is actually executing their code against hundreds of different machines. And how you start to find out, when they've an inconsistent experience, what went on, and how do we make it better, is a huge big data problem that is very hard to analyze for us. One key customer pain point with Lambda is the idea of a cold start, that there isn't an existing hot sandbox sitting there waiting for their execution, which causes a delay when they execute their invoke as a sandbox is populated with the necessary runtime and code to execute. And we work to constantly drive down and minimize those cold starts, but how we understand what they're happening so we can go after the next layer of them is a problem space we have. Secondly, customers can experience variance in execution times. And we don't want that. We want consistency. But these problems are very hard to answer when you're dealing with a data set that's happening in a very tight time period across hundreds of different machines out of a fleet of many, many times that. So what did we put together to deal with it? First off, on the front end of Lambda, we have a fleet of thousands of hosts that are processing, sitting behind load balancers, that are processing each and every invoke that comes in by a customer. Those hosts produce service logs. And we do a little on-host aggregation on the EC2 hosts. There's nothing serverless about this yet, but we're just breaking down the data in the service logs, doing some per host per period aggregation. So we're getting aggregated records as to what went on the host. And we push that out to Kinesis, pretty much the very first design pattern we discussed earlier, that of the streaming transformation. So Lambda Stats was built in about 2 days by a developer who needed to solve this problem. And that talks to the power of cloud computing. So you can stand these things up really fast, you can add a lot of value, it scales seamlessly, it's great. And here's quickly what we put together. So we took those service logs, we fed them to Kinesis as I described. We used Kinesis to push into a Lambda aggregator, again, just as we described in the first design pattern we saw earlier on. We fed that into Elasticache. And what this diagram doesn't represent is, again, you have many thousands of these front-end servers running, each of them forming this first part of the workflow, and all of them pushing into Elasticache. So at this point, you've got the kind of reduction after the fact. As you take all of those entries that are flowing from the thousands of front-end hosts, we trigger another Lambda aggregator, and we trigger it using a periodical, which is the second design pattern we discussed earlier, to take the records that have arrived into Elasticache since the last time we executed and perform aggregation against those. We push those into Firehose, again, because we want to smooth out the burstiness here. If we're running on a period, depending on how much data has come in that last period, since CloudWatch events triggered us beforehand, we'll have varying amounts of data coming out of that second Lambda aggregator. So we want to smooth that out, that burstiness out again, before we start pushing it on further in our data pipeline, which is why we tend to put another Kinesis stage in here. And in our case, we push it out to two sources. We push it out to Amazon Redshift, because we want an SQL queryable interface to start to hunt through this data and look for patterns to help us solve those customer problems, which is the key issue behind this. And we push the aggregated raw data into S3 so that as we start to find bits we're interested in from that Redshift analysis that our engineers might do, we can go and hunt and pull out the real logs backing it to help us dive in and understand what the problems look like. So 2 days of work, give or take, a pretty compelling data pipeline that is scaled for 1.5 years with the massive growth that Lambda undergoes. And this is the amount of code that backs it. So this is the first phase and how easy and powerful these things are put together. We're just pulling data. We're just taking data as our input. We've defined our Redis host where we want to put our data afterwards. We do some simple aggregation on this data, and we push it out to Redis. And the idea is that one of these is called with every single log push from every single invoke service host in parallel and crunches that data, depending on whether it's a Sunday night, which is our low point, or a Tuesday afternoon, which is our high point, and with the significant variance between them, with absolutely no maintenance on our side. The second phase of it, with that CloudWatch events, as we discussed, triggers this second Lambda to pull from Elasticache and push us out to Kinesis Firehose again. So again, much as we looked at with the MapReduce example earlier from the AWS repository, here again is about 50 lines of code, give or take, which is performing an incredibly powerful set of data aggregation and reduction that scales seamlessly. And that's what serverless data pipelines are about. So this is what we built. I want to move on with it to look at what happened after the fact. Because we built this in a rush, it gave us a huge amount of value, but we definitely made some mistakes along the way. So the kind of problems we look at, in this case, we have a customer with the concept of high leaked workers, as we call it, which means we're seeing a lot more sandboxes on the back end being used to execute the functions for this customer than we would expect in an ideal world. And looking at the data, we see these weird drops and spikes, and maybe that's exposing a bug in our algorithms, which is causing us to schedule incorrectly. We took a look at the front door at the ELB logs coming in before Lambda itself ever gets hold of this stuff. And we found this, which is the lack of the same spikes, and this data should roughly match. So in this case, while we had the right operational telemetry around Lambda stats, is the service running, is it pushing data, that kind of thing, what we were not correctly monitoring was, is it dropping data? And that was the reality of what was happening here. So as we dug into this one, we found it wasn't, or independent of the original problem, we found that we had a problem with our statistics gathering service that we had come to rely on. And that's key lesson number one, is that you've got to put your monitoring both on the consistency and of your data, as well as just your operational. Is your service running? Is it responding? Is my latency okay? Is it scaling okay? So what was happening? Lambda had been growing rapidly. Lambda stats had been running for about a year, and we'd got to the point where we were overloading Kinesis, that we were dropping data at the first stage of this pipeline. The number of pushes we were doing into Kinesis, it wasn't able to handle them. So we fixed that by increasing the batch size we were pushing to Kinesis, essentially doing less calls. The front-end fleet had probably tripled in size in the time since we launched Lambda Stats, and it was simply too many pushes to Kinesis. By updating the batch size, Kinesis started to play ball, and all of the data started to flow into our Lambda aggregators okay. And it completely overwhelmed Elasticache once we did. The data was still arriving in Elasticache, but we suddenly started to watch ourselves drift minutes, hours, and we even got as far as 3 days behind reality before we got on top of this one. So what we had to do was we had to shard the data set. And this is relatively scalable. I think we're sharded to 5 at the moment, but we have alarms around this as to when we potentially start to see problems again, and we can just continually shard this data set over more and more Elasticaches. And those Elasticaches will each trigger, Lambda aggregators, which the remainder of the data pipeline should continue to flow. The main point I'm getting at is you're going to need monitoring on each stage of your pipeline. Monitoring both the latency and availability of the components of the pipeline, as well as the data quality, which is the piece we missed because we built this one fast. Okay, so this is a summary of everything we've just discussed for the people who read these slides on the internet after the fact. But what were the key lessons learned? I mean, the obvious one I've called out is you should collect drop data at every stage. And this seems like 101 duh stuff, but the reality is we missed it as much as everyone else on this particular one. We've built tons of other systems where we remember it. And the fact is that when you're moving fast, you're going to make mistakes. So hopefully you guys can avoid this one from this story. Replayability of data is another key one that we took from this. That, learning that lesson as we drifted behind and fell ultimately 3 days behind. In this case, Lambda Stats was able to replay the data, but it would have been a world of pain if we weren't, because you have to have that consistent window of data to be able to query over after the fact, or else you're in trouble. Finally, something else we took from this and kind of added as a tenet for the building of future analytics systems is that, when you have tons and tons of data, it gets great that you can aggregate and you can mash different things together to more and more levels of abstraction. But sometimes you can go too far and you get to the point where you can't even explain why you have the data you have. And we have found in some of our systems that problems in the data, you get weird stuff, you're trying to explain why it happened, and you start getting to the point where you're questioning the data as much as everything else. So therefore, something we've added in and that we review as we're contemplating what levels of kind of aggregation we perform on the data we want is that it must be explainable. We must be able to clearly map back to the basic inputs of our system what this aggregated data means. And that puts us on a much better place, we found, in terms of building systems that are scalable, sustainable, and continue to add value for us. So Lambda Stats is the example of something we built fast. We learned a bunch of lessons. The second side of it is using those lessons, we came back to building some more serverless big data analytics pipelines. And this time we very much designed in advance. We took our time. And the Lambda tuning pipeline is the second system I want to discuss today. In this case, the use case is we wanted to leverage past function performance of customers' function executions to predict future function performance and schedule it appropriately to optimize execution and deal with that problem of any variable execution, basically trying to scrub that out. Again, the cold start experience. If we know things like how long a function is going to execute, how much resources it's likely to consume, not relying on just what a customer has asked for, but what the function tends to use, we can do a much better job of giving a more consistent customer experience to executing those functions. So we're going to use some of the design patterns we discussed earlier in doing that. So in this case, we start out again with our Lambda invoke service, and we're going to use the same Lambda Stats Redshift data store we had from the last time. And one of the key architecture decisions here we had was, did we want to try and re-architect the existing Lambda Stats pipeline we've just talked through, or did we want to take another approach which allowed us to move faster with less risk? So ultimately, the data we want is coming from the same service, but rather than having to go and rebuild the entire service we have that is largely working, despite the few glitches we discussed earlier, we were simply able to pull another source of data out of the invoke logs and trigger a CloudWatch event per function. Because what we're interested in here is the per function performance, whereas what Lambda Stats has is only the aggregates. And very simply, by pulling an event out of an existing service, we can augment the existing data store we have with another aggregator and get a very different view on the data and build another data pipeline. So this is a kind of more advanced design pattern or advanced approach, which again allows you to very quickly and very safely, without having to go re-engineer your existing systems, get a lot more value from them. And again, with a similar pattern, we push this out to another S3 data store in DynamoDB index. And what we're pushing out is using historical data from Lambda stats plus what has gone on in that current execution of how much resources that duration that function consumed versus predicted, we're pushing in likelihoods of how long this function will take to run, how oversubscribable it is, all that kind of stuff that we can use to make more optimal scheduling decisions for future invocations. And what we do is we take that data store and we push it into another Lambda aggregator. We feed it into Elasticache so that all this data is there on recent customer executions with the latest predictions we have from that aggregation. And we pass that into the Lambda placement service that actually makes placement decisions about where to put sandboxes within our fleet. So if we put all of this together, we have our Lambda stat service at the start. We add in the Lambda tuning pipeline that gives us our second source of data. We pass this into the Lambda placement service. And there, end to end, is a big data analytics pipeline, which helps us make decisions on what is a massively complex distributed scheduling problem. And by having that additional data from this pipeline, allows us to make more sensible decisions. Okay. So the final piece of this, though, is that this is a serverless pipeline. And this is definitely the kind of powerful thing that we expect our customers to be able to build. But we have one admission here that as we came to actually contemplating putting this live, we weren't willing to place the efficiency of Lambda scheduling based on Lambda. Because if Lambda starts to fail, and Lambda scheduling starts to get worse as Lambda starts to have a problem, and if Lambda gets as big as I think Lambda is going to get over the next decade, the world will probably end. So we ended up putting these two key pieces onto EC2 rather than Lambda, not to take that circular dependency. It was really easy to do because the code just runs. You know, whether your code is a Lambda handler that executes serverlessly or whether you place it on a traditional instance, you can run exactly the same code. And that, again, is part of the compelling power, that whether it's an ECS container or a raw EC2 instance or a Lambda function, you can, to a large extent, execute the same code in all places. And so that because we're talking about serverless applications, we'll leave it like that here for today. So that covers the first half of what I wanted to talk about today, which is kind of the big data analytics side, what we're seeing customers do, what we've done ourselves. The second part of what we wanted to talk about today was machine learning inference. Because serverless is a really compelling platform for doing machine learning inference. Machine learning consists of two phases. There's the training phase, where you're building your model, which is a lot of heavy-duty number crunching. You're going to want to do something with a lot of GPUs. It's not the sort of thing you're going to do on a serverless platform. You're going to use something like Amazon ML, MXNet, or TensorFlow to do that crunching. And what we see a lot of people do as they get into this new space is they tend to use those same instances for doing the inference after the fact as they used to build their model. And it's a very different problem space. In fact, in this case, you have a much lighter level of compute. You want to be more scalable because you don't know what volume of inputs you're going to get. So this is one that's much better suited for Lambda. So let's talk about a much easier workflow that we're going to see today. How to build a machine learning inference on Lambda. Because it's a lot easier than it sounds, and I wanted to walk through what's involved so that we can show you, it's not hard, and you can get a lot of value from it easily. And then we'll circle back and show again how we've used this internally on some of our tools. So first off, we're going to take an Amazon machine learning model in this case. We're going to build a Lambda function, or build a bit of code first to read from that model. We're going to manipulate the Lambda function to do the correct input and output that API Gateway expects from that function. enable the trust we need between Lambda and API gateway to call it. And we create an API. Sorry, I'm ahead of myself. And this sounds like a significant list of steps, but it's quite easy. And it gives you a massively scalable way to read from machine learning with no underlying servers or maintenance of that pipeline. So let's take a look first at what's involved in actually reading a machine learning model. I've used Amazon ML in this case. I've avoided doing anything fancy with the model because I want to focus on the inference side. That's what we're interested in here. So it is a couple of lines of code to pull what we need from a model and to do inference against that model, just passing in the inputs to our function here directly to the ML service to do that inference. In terms of how we make this work, you can create a Lambda function with 2 calls. And we'll do this in real time in a few minutes. You can call that function, and at the bottom, there you have the results from your ML model, giving the prediction of 33% in this case likelihood of actual success. That gets you a serverless query to your machine learning model. But it doesn't get you something that's scalable and something that's easily accessible through a web interface or anything like that. To do that, we need to put it behind API Gateway. And to put it behind API Gateway, we need to change both the inputs and outputs to our Lambda function to make that happen. And again, this is super easy stuff. Basically, you need to add a couple of lines of standard code to the front of your function, which will just tell us where we're getting our input from, depending on whether we're getting called from API Gateway or whether we're still getting called directly from Lambda. And equally, you want to push the correct kind of JSON response that API Gateway is expecting out of the bottom of your function. Finally, you need to put a trust relationship in place between API Gateway and Lambda that allows API Gateway to call your Lambda function. And that is done from the command line or from an API quite easily as well. So in two statements, you can create your function, and you can add the appropriate trust between API Gateway and your Lambda function. So that brings us on. We have our machine learning model. We have our Lambda function. How do we actually create the API Gateway pieces we need to complete the stack here and give us a scalable web-based input into the Lambda function? And this is the standard console interface to API Gateway where you define your API. And there's other systems like Swagger and that kind of thing you can use to manage this whole thing. But I just wanted to walk through the basics here initially first as to what are the steps involved in creating an API. Because the problem is they'd look like too long and scary a list when you actually look at it. This looks like a pain. You have to create a REST API, get resources, create resources, put methods response, put integrations, and create a deployment. So I wanted to walk through, really, that it is not that painful and what is involved in actually doing that. So starting out of the console, I said we were going to take a basic model that we weren't going to worry about the complexities of the model. So using the standard Amazon ML intro tutorial, if you go through that, you will end up with this model, which is, it's a model of banking and market research data, which tells you, based on various inputs you might want to give it, the likelihood of a customer responding successfully to market research query. So it's not particularly complex stuff, but this is what we have. And we have Lambda. So let's look at what's involved in what we were talking about earlier. So looking at the same code we looked at earlier, very simply, we have our standard interface that is this getting called from API Gateway or otherwise? We have the same small piece of code we looked at to actually talk to our machine learning model. And equally, on the tail end of it, we wrap it up in the correct JSON structure and push it out again to API Gateway. With that code, I'm just going to walk through the steps involved. So that's just testing that it actually works. So here we are. We execute that Python code. In this case, sorry. Oh, man, hold on. Sorry about this. So it actually invokes the service. It tells us what is, there's our prediction having come back. So we take that and we create a Lambda function with it. So we're simply pushing that function up into Lambda. We've created our function here, 128 meg function with Python, and it'll read the EML intro model. If we now look here, we have our function in place. And here's an opportunity to see what we have launched this week. This is the new Cloud9 console. So you can now see, edit, and debug your code in real time. We can see the Boto libraries that we're using with Lambda. And we can see the same piece of code we just looked at on the terminal now there as a Lambda function. So now let's take the API gateway piece. Or let's prove this works first. So the final piece we wanted to do was we wanted to add that permission to talk to API gateway. And then we want to actually invoke our function. So there's our function has executed, and here's the output that comes from it. We've got a prediction score that based on what we gave it is someone who's divorced and somebody who has an age of 32 has a likelihood of 0.33 in responding based on this particular model. So that gives us the first part of the piece. It gives us a serverless function that can talk to our machine learning model. Second part of the story is what we want to do to hook this up to API gateway. So again, I'm just going to walk through what's involved. So with API gateway, we want to go through that first phase of what we looked at on this other model, on this. Initially, we want to just create a REST API, and we want to create resources attached to that. So coming back to here, that's all we've done. We've created and defined a model called our market research query. By default, we have to define an initial path of slash, but we want to define a URL that we're actually going to query this off. And we're going to define a slash query in this stage, in this case. And now you can see that we should have the one clunkiness with this. That's interesting. Okay. It's not what I expected to see, but it looks like we have a lot of these for some reason. Sorry about this. But such is demoing live. I have no idea which one of. All right, we're going to take 2 minutes. We're going to clear up these APIs very quickly so that we can do this correctly. Oh, cool. No, we're not. All right. No problem. We're going to run this again anyway. And we're going to create our API as we've described, and we're going to figure out which one in that UI it is. We're going to do the second piece of this, that as well as creating the API and just defining the slash query, we're going to define resources to go with it. So for the Lambda API, if you're doing a Lambda end-to-end connectivity like this, you have to use a post. It's the only thing that Lambda supports. You can't use a get. So we define a post interface to this, and we get an ID of that post interface attached to the API gateway. And with that, we define responders as to what we do for each of those methods. So we define that there's a put method response of 200 to each of these. And then we define an integration against that, which is we're literally saying that, for a post put to this query endpoint we've defined, we now connect that to the Lambda function we want. And we pass in whatever comes through the front door. So it's quite simple stuff. It looks like a whole bunch of commands, but what I'm trying to get at is it's actually super easy to set all this stuff up. And it's quite well documented within the AWS SDK. And at the end of that, you just simply do a deployment of the API you've created. What that gives you is that I now have a URL that I can simply invoke against with the same kind of arguments again. And out the other end of that comes the same predictions that we had earlier, talking through Lambda, through my serverless stack, to the machine learning model behind it. And the nice piece about this is you can stick Route 53 and an ALB in front of this, give it a DNS name to make it nicer than the kind of URL we're calling here, and then you've a seamlessly scalable machine learning inference engine. It's super cheap, you only pay for what you're using, and it's super easy to set up. So let's go back and talk again within Lambda what we've done with this kind of model. So we're coming back to our placement problem again. And so far, we built a system which gives us a lot of information on placement, on what a function is likely to consume, and what that might do to help us decide where to place it. We also want to understand how much a customer is likely to call a function. One of the key pain points for customers is they're often bursty in their use of Lambda, and that they might call hundreds of invocations, or they might call one. And each time we receive an invocation, if there isn't a sandbox present, we're going to have to spin up a sandbox, and a customer is going to take that cold start hit. But customers have patterns of behavior. Sometimes they tend to follow a cycle, and we can build a model with that. And what we built is a model to help us understand what is the likelihood that we should spin up many more sandboxes than just the invoke we've received from this customer. Because if we can get ahead of that curve slightly and start pre-populating those sandboxes with the environment and the code the customer wants, as they ramp up, they're much less likely to receive those cold starts. So, sorry, what I've just talked through. So in this case, we're going to use some of the same design patterns we looked at before. Our input this time is the DynamoDB index that was the output of our Lambda tuning pipeline. In this case, we have used Lambda again, because this one won't end the world if it starts failing. It'll just mean that customers get a bit more latency if we start having problems with Lambda. We use an Amazon machine learning model, a much more complex one than the one we just looked at, to make the decision of what is the likelihood that this customer is going to do many invokes rather than just this invoke we've seen. And we pass that information back into S3. That model comes from S3, and we pass that information back into the same DynamoDB table. And essentially what we're doing is we're augmenting a column in the DynamoDB table. Our trigger point into this system is entries getting updated or added to that table. So what we have is, as we feed data into that DynamoDB table from the Lambda tuning pipeline, magic happens, and that data gets automatically augmented with additional information from the machine learning pipeline if there is sufficient information in the model on this particular customer or function. So how does that play with what we looked at earlier? We see this completes the story here. And somebody really messed the alignment of my slide. So this is finally pretty much where we stand today. We're going to continue to obviously evolve these kind of pipelines as we seek to optimize what we're scheduling for Lambda and how we can continue to more efficiently schedule things and drive down cold starts, guarantee better execution for customers. So that's the end of the story here. I'm about 5 minutes ahead of where I intended to be, but that's as much as I had to talk to today. So I'll ask for questions at this point. Sorry, I'll go back and let people take photos. I saw the cameras up there. Sorry, increase which?
The execution time of 5 minutes.
So the question is there any plans to increase the execution time of 5 minutes in Lambda? You've seen this. Yes is the short answer in the long term. You've seen us this reInvent announced 3 gig functions, which is the start of a denser compute roadmap. We want to make functions bigger. We want to make them longer, but it's coming eventually. It's a fair point. It's something we're working on for Lambda, is the short answer, so it is coming. But you are right. It's because we replaced it with EC2 here that is feasible in this case. But Lambda from SQS is a key customer ask, and it's definitely something we're looking at. Hi.
So for the flow between DynamoDB and your Lambda aggregator, how are those Lambda functions triggered?
There's a DynamoDB trigger you can define. So on either create or update of either an object or even a row or column within DynamoDB, you can trigger different Lambda actions. It's quite fine-grained.
Is that typically per row or per batch?
You can do either. That's the mechanics of how the read happens, but the trigger you define is on create or update or whatever you want of the DynamoDB object that it will trigger a Lambda. The mechanics of how it happens is it's fed out through a stream, which is what you read from in your Lambda function.
Can you talk to a little bit about the MapReduce function in the S3 solution versus spinning up a cluster?
So the question is, can I talk a bit to the MapReduce function and the S3 solution as opposed to spinning up a Hadoop cluster to do it? What do you mean by talk a bit?
Comparison is a Hadoop killer or Spark killer?
There are different use cases for each, and it depends on the complexity of the reduction you have to do, fundamentally. We're back to talking about that you have a 5-minute execution time on Lambda, and Lambdas tend to run on essentially a single CPU core for the most part, although with 3 gig functions, you now get into multi-core territory. So, it depends on what you need to do in your reduction. So no, it's not a Hadoop killer. There are definitely use cases where you have large data sets that you need to do quite intense reduction on, and basically you will still get better performance today from a Hadoop-based environment for those use cases. But there's a huge amount of MapReduce, which both tends to scale up and down, which is where Lambda comes into its own. If the input to your MapReduce tends to be highly variable, you don't have to provision for peak like you would with a traditional Hadoop cluster. And secondly, that the reduction isn't as complex, so running it in a serverless pipeline makes a lot of sense. Okay, I'll go here first.
It's a question about Lambdas. I heard each implementation of Lambda will require a new IP address, which is an issue if you're running it inside an VPC. My question is it IP per cold run, or is it per actual invocation of each Lambda?
So the question is that each invocation of Lambda gets a new IP because it potentially runs on a different instance. And you asked, is it an IP per invocation or per cold start? You have to treat it when you're writing your code like it's per invocation. We will attempt in our scheduling to optimize to existing hot sandboxes to try and minimize those cold starts. Therefore, there's a high likelihood if you're just doing a sequential bunch of Lambdas that you'll continue to land on the same sandbox. But you cannot guarantee it. And particularly at high scale, if you're doing a lot of invokes, or if you've high concurrency, you'll actually be partitioned across different portions of the fleet at the back end. So you'll be load balancing across those. So even with sequential invokes, you may find yourself just landing on different pieces. So from a coding perspective, you have to assume the worst.
So this is on machine learning inference and lambdas. They take an event as like a JSON formatted object. Sometimes the inputs into machine inputs are very, very complex. So what's your recommendation on shoehorning into the event?
Sorry, so the question is that the inputs for machine learning can get quite complex, and JSON is kludgy for doing that. I don't have a good recommendation there. I mean, as much as I've done when I've been writing my code, is I tend to end up with some quite large JSON blobs. But
Think serializing might do it, or
Yeah. I don't have a good answer off the top of my head here because I haven't run up against the kind of 6-med limits of JSON blobs that will cause that to be a problem. Serializing would be the first place I'd go and look if I was there, but I can't give you a good recommendation is the short answer on that one. Well, this is the Lambda Stream APIs. Yeah. Yeah, I mean, his concern isn't about how to do it, though, is what I'm hearing. It's the complexity of managing that JSON blob and what you have to do in code to maintain that, I think, more than anything else.
Say you have like 500 features going in, as inputs, things like that. You know what I mean?
Yeah.
Right. You have to be able to supply that as an input in a JSON format, which is complex. So.
Yeah. I mean, you tend to build a data structure, a hash table of some sort that, you have a function that converts that to JSON, so you're maintaining a data structure rather than maintaining a JSON blob, and you just push that around as needed.
I was wondering why you chose to partition Elasticache instead of using something that like auto-partitions, like Dynamo, for example.
Speed on the other side of the querying, it's not a stateful data set. It's more acting as a buffer just to collect. So you've many thousands of invoke hosts pumping into this Elasticache. The purpose this Elasticache is doing is it's collecting that data from many hosts so that the next stage of the Lambda aggregation can do the aggregation across all of the hosts for a given time period. So it's not stateful, it's not something that's long-lived. Yes, we could have approached it with DynamoDB and a TTL to clean up afterwards, but I don't know that we need to go there. Elasticache is much faster. Yes, DynamoDB with DAX would be as fast on the read path on the far side of it, but it would be much slower on the write path. You're talking about multiples anyway of the difference in latency between an Elasticache write and a DynamoDB write. You're talking 10x at high percentiles. So again, what we want is this data pipeline to be fast, to push large amounts of data quickly. Elasticache fits the need. I get the partitioning question, but maintaining the Elasticache where we get our millisecond read and write is what we want here, rather than looking to something stateful that we wouldn't have had to shard.
Maybe that's a new feature or service. Auto-sharding
Elasticache does do auto-sharding. We just wanted to control the sharding in this case, because we have knowledge of the structure of that data, that we could guarantee the evenness of the shard and that kind of thing. So go ahead.
When in one place you are reducing the bursting, you're using Firefox, and in one place you're using FQS, like from CloudWatch to FQS to that aggregator. I'm just curious to know what device it is. Why not Firefox?
Volume of data more than anything else. This is just a simple list. Sorry, the question is why use SQS here rather than Firehose in this particular example of where I'm pumping into Lambda. And I've already been called out that I'm actually, the only reason SQS works there at all is because it's EC2 rather than Lambda in this case. I actually don't have a great answer on this one, to be honest. I mean, SQS is easy and does the job fine in this case. It's just a very simple, naive list. It's not a large volume of data. So really what we're just doing is using that list to identify what we need to pull from Redshift. It does, yes. Yeah. You could. That's the beauty of it. There's a lot of options here. Sorry, go ahead. You've been waiting for a while. I don't know. What we have now is an internal tool that we built fast that added a lot of value. Why I felt it was a good thing to talk about here is it's a great example of what the cloud kind of does for you. It allows you to build these things real fast that are powerful. Because it was built real fast and that kind of thing, it definitely wasn't properly designed as well as it should be. So what we are going to do is go back to the drawing board on that one and build something that, yes, what are the customer use cases, all of that kind of thing. And so yes, we've just funded a team to go and tackle that. So yes, it's something we're thinking about in the long run.
Do you, I know my traffic is wait in the morning until afternoon, and in the night I want to show it. So if I can suggest them, okay, prepare, warm up some distances and set the traffic so that the traffic is coming.
I'm not going to be able to tell you what we are or are not going to do. It's definitely a constant ask from customers, hey, if I can give you some heads up on what I'm going to do, can you make that happen? So I think we have to go there in some fashion. We definitely, we've purposefully kept the interface to Lambda very simple. You only scale in a single dimension. There's not a whole bunch of knobs you have to tune. And we want to try and continue to move down the simplicity path to enable more people use Lambda rather than to add a whole bunch of configurables and that kind of thing. But at the same time, I'm conscious that there's two particular use cases we hear a lot from customers. There's one, can I tell you what I'm about to do because I know what I'm about to do so you can prep for it. And there's two, I have Lambdas that I don't care how fast they run, so can I tag a function or an execution for, run it within this SLA and I don't care and maybe run it cheaper. So there are definitely two places we hear a lot of feedback that we're going to be thinking long and hard about. So the answer is the time limit still 5 minutes, although we've increased to 3 gig? Yes, the time limit is still 5 minutes at this time. We do not face that with these, no. And I mean, we design and cut up what our Lambda functions do appropriately, such that we know we're not going to hit that, and that we're essentially calling one Lambda function per second per invoke server, and we know we're not going to process enough traffic for that batch of data to take any longer than about 1 minute, never mind 5 minutes. We kind of hold our monitoring on execution length is around the 1 minute mark. If we start exceeding that, we'll have to revisit this architecture. So usually, it's about chunking your algorithm such that you're not going to get there. I fully appreciate that we need to enable our customers to do longer execution, but it's not something we have at this time. You've been waiting a long time, I'm sorry. Throttling because you have too many concurrent rather than too many. We don't throttle on invocations per second. We only throttle on concurrency. So how many lambdas you have executing at the same time is the piece that gets throttled. Hmm? Yeah. You're not getting lambdas invoked because you have too many that are currently running based on your concurrency limit. So what we're throttling on is how many are running, not how many invocations per second you're doing. Okay. They don't. They return to you with a 429 or something, I think, is how the customer sees it on their end, that you've exceeded your concurrency limit. The concurrency limit by default is 1,000 in most regions, it's 3,000 in US East 1, but equally, there's customers who are many, many times beyond that. Why we have those limits in place is we'd like to engage with customers who are getting beyond those limits, so we can ensure they're doing the right things and that they're using things in the right way before we let them get much bigger. But if you have a real use case and you're hitting those limits, like reach out to your TAM or reach out to us. We're happy to make those limits a lot bigger. They are not hard limits. They're there to just stop customers doing crazy things more than anything else. Okay. Yeah, I guess so. We've been asked to move to the hall because they've got to tear the room down and reinvent is over, so thank you very much.
Sure.